We're all ready for our presentations. This is Jessie Muir, and she is an assistant professor. She's an assistant professor in the Department of Physics at the University of Cincinnati. She works on research at the intersection of cosmology theory and data analysis with the goal of using measurements of the large-scale properties of the universe to learn about fundamental physics. And let's see, originally from a suburb of Detroit, she completed her undergraduate studies at Michigan State University, master's work at the University of Cambridge as a Marshall Scholar, and her PhD at the University of Michigan. And for the last couple of years, she's been interviewed about dark energy science for Astronomy Magazine and astronomy.com and Scientific American. So without any further ado, it's Jessie Muir.
Hey, thanks you all for having me. I'm really excited to be here. So I just started at UC this past fall, so I'm new to the area. This is my first time at the observatory. So when people raise their hands for here, me too. So I'm going to talk to you today about some of the science that motivates the research I do with galaxy surveys, and a little bit about what that research looks like. So, you know, in astronomy, we think about looking at these beautiful star clusters of beautiful galaxies. I spend most of my time thinking about stuff we can't see. And so that's what we're going to be talking about today. And to help motivate that, well, in addition to talking about the science, I'm going to subject you to a number of cartoons I've made of varying quality. But to help situate this, a lot of this is a pie chart showing basically a picture that we have of the universe that we put together as a scientific community from several decades of different kinds of observations. And what the pie chart shows is our best understanding of what the matter and energy composition of the universe looks like. And the really striking thing about this pie chart is that it's only this littlest sliver, which is about 5% of the mass and energy of the universe, that is made of stuff that we really know how to describe on a fundamental level, stuff that's made of protons and electrons and neutrons, things that we can write down particle interactions and know exactly how to describe things that was like seen in the lab on Earth. So that includes, you know, every star in every galaxy, everything on Earth, TV screens, astronomy enthusiasts. That's only 5% of the stuff in the universe. And the rest of this pie chart carries these, you know, mysterious sounding labels, dark matter and dark energy. So I'm going to talk more for most of this talk about what these are or what we're trying to do to learn about what they are. But sort of the very brief overview is at about 25% of our cosmic pie, dark matter refers to some substance that interacts through gravity like matter. So we can see how it influences visible matter, so this little 5% slice. And through that, we can tell that it clumps up into structures, it orbits the center of galaxies. It doesn't seem to interact with light or other forces, or if it does, it must be very, very weak because it's invisible, we don't see it. The biggest piece of the pie is labeled dark energy. That's about 70% of the matter and energy in the universe. And this, and I'll get into this in a little bit more detail in a minute, is basically the name we give to whatever is causing the expansion of the universe to accelerate. We don't know what it is, but to get that behavior, it has to have some very strange properties. One interpretation is it's something acting like it has negative pressure. So that's not a very intuitive statement. Everything else we interact with has positive pressure. If you have a balloon full of air, you squeeze it and increase the density, the pressure that it pushes out against you goes up. That's positive pressure. Negative pressure is like the opposite behavior. So like you would push on a balloon full of dark energy and it would compress, or you pull on it and it wants to keep expanding. Very strange stuff. I'll get into a little bit more about that. The key thing I want to note here is that, as I mentioned, this pie chart picture is something we've constructed with a number of different kinds of observations. And we have pretty compelling evidence from a bunch of different observations, some of which I'll touch on in more detail in a minute, that these things are here. but we really don't know how to describe them at a fundamental level, and that is really dissatisfying. And we would like to work towards that. So most of what I do and the work that I do with collaborators across galaxy survey efforts and basically these are some of the biggest open questions in physics today that as a community we're working towards learning more about them. So this is the outline of the talk. So my plan is to spend a little bit of a time talking about some of the evidence that we have for the fact that dark matter and dark energy are important components of the universe. So I won't be completely comprehensive here, but I'm going to kind of focus on like what were the first observations that kind of convinced us as an astronomical, as a cosmological community, that there's really something going on there. I'll give a little bit of an overview of some of the approaches we take using maps of galaxies in the universe to try and test different models or to test the properties of dark matter and dark energy to try and learn a little bit more about what they are. And then, time allowing, I'll tell you a little bit more about how we, some analyses that I've been in particular involved in one observational effort called the Dark Energy Survey, how we approach this using that survey. And you'll notice throughout this, I've got a few acronyms for different surveys. They all have very similar acronyms because they all have dark energy in the name. So we're not very creative, but we're very enthusiastic. All right. Okay, so not exactly the first evidence for the presence of dark matter, but the first evidence that was like clear-cut enough that it brought the sort of astronomical community on board that this was something that had to be there. The first evidence in that sense of dark matter is from observations of galaxy rotation curves, which means that the rate at which stars are orbiting the center of galaxies through measurements made by Vera Rubin, who is pictured here. And so she made these observations in the 1970s. And just to illustrate a little bit about what that is, we're going to do a thought experiment with a yo-yo. If I had planned ahead of time, I would have remembered to bring a yo-yo and I'd swing it around, but you can picture how this would work. So you're using a yo-yo incorrectly. You're just holding the string and swinging it around. And when you're doing that, the force, the tension on the string is keeping that yo-yo going in a circle and not like flying across the room and causing havoc. And if you're swinging it slowly, you can kind of hold on a little bit loosely, and it's a little bit of a leisurely exercise. But if you want to spin it really fast, the faster you swing that yo-yo around, the tighter you're going to have to hold on to that string, because the stronger the tension, a stronger force is going to be required to keep it going in a circle and not flying across the room in a straight line. So the exact same idea applies to looking at stars going in orbits around the galaxy. So in this case, instead of a string holding a yo-yo moving in a circle, our metaphorical string is the force of gravity from the mass inside that star's orbit attracting the mass of the star. And so that inward pull of gravity is going to keep the star moving in an orbit instead of flying off away from the galaxy. And that means that if we look at the rate of the orbit of stars, how fast stars are moving around a galaxy, that tells us something about the amount of mass inside that orbit. Because if there's more mass inside the orbit, that means there's stronger gravitational force, because gravitational force is proportional to the product of the two masses involved. So here it would be mass of the star and mass of the stuff inside the star's orbit. And so more mass inside the orbit results in faster orbits for the stars. And this is depending on their radius. So, first look at a galaxy light from stars. A good first guess of where the mass in that galaxy is would be that it tracks the light that we see. It tracks the visible matter. And you can make a prediction for if all the mass tracks the profile of the visible matter. You can predict in my very roughly drawn cartoon that as you move out from the center of the galaxy, So as you move out to look at the orbits of more distant planets, their orbital velocity will fall off in a predictable way. And when Vera, Rubin, and people since have observed the orbit of gas and stars in galaxies, we don't see it falling off like this. We see it being kind of flat with radius. It doesn't fall off, which to make that work, it means you need more mass in your galaxy, and you need to keep having more mass. Basically, as you move out, you have more and more mass inside of there. And the sort of physical picture that makes this work, which is not showing up on my slide, maybe because I didn't include it in the cartoon, is that if your visible matter is nestled in a much larger halo of some invisible matter that extends well outside of that where the stars and gas and dust are. And you can look for, so this is something that's seen pretty universally in galaxies. It's also a similar behavior you can find if you look at the motions of galaxies and groups of galaxies. And you find that, if I'm remembering the percentage right, which I should just know intuitively, only about 20% of the matter in the universe is visible, like stars and gas and dust. And the rest of the mass that's involved in these orbits is this invisible matter, which we name dark matter. So this is one of a number of pieces of evidence for dark matter. This is sort of the initial hint that there's some invisible source of mass there that's interacting gravitationally. All right, so that's a crash course into how we discovered dark matter. Next up is dark energy. And so to put into context how we learn about dark energy, we need to start with the fact that the universe is expanding. So this is when we look at the properties of the universe on very, very large scales, and we look at how distant galaxies in the universe are moving relative to us and to each other, we actually see that if we look far enough away, basically all galaxies are moving away from us. But we're not like in a special place in the universe in that sense. If you map things out, it's all galaxies are moving apart from each other. I'm simplifying things a little bit here. Galaxies that are close enough to each other, like the Milky Way and the Andromeda Galaxy, are actually falling towards each other because they're close enough to interact pretty strongly gravitationally. But when you look out at large enough distance, you see this overall expansion of space. So the average distance between galaxies is getting bigger and bigger over the history of the universe. And this is something that we've known since the 1920s. So I guess we're at a centennial of this knowledge about the universe. So one of the big discoveries of Edwin Hubble, the Space Telescope is named after, was figuring out that galaxies are moving away from this in this uniform way. And this cartoon here sort of illustrates how to picture this with the 2D surface of the balloon as the analog for like the 3D space of the universe. So as the balloon is stretching, the individual galaxies are not growing, but they're getting more and more spread out as that surface of the balloon is stretching, or in our universe as space itself is expanding. So that's the fact that the universe is expanding. We start to learn about or to move towards how we discover dark energy. We have to think about mapping out how that expansion has changed over time, or as we often refer to it as the expansion history of the universe. And here we're going to use a neat feature from special relativity that light travels at a finite speed. And it means that looking out at the universe is effectively a time machine, right? The further away you look at an object, the longer it took that light to travel to get to you. So when we look at more distant objects or very distant galaxies in the universe, we're getting images of what the universe was doing at earlier times in its history. Okay, this is a faint line. I'll read it out loud for those in the back here. But this means that we can track how the universe has expanded over time by looking at relationships between the distances to astronomical objects and their velocity, how fast they're moving away from us due to this cosmic expansion. So the velocity is something we can measure by looking at the spectrum of objects, looking at the colors. Because of Doppler shifting, when things are moving away from us, the wavelength of the light gets stretched out. We can think of it, the expansion of the universe stretches that wavelength out. So things that are moving faster away have their color shifted towards the redder end of the spectrum. So we call this a cosmological redshift. And so we can measure that if we can measure the spectrum of, say, distant galaxies and see features in the spectrum that we know correspond to certain like atomic or molecular lines. We use that as kind of a barcode for, like, we know from a lab that this set of lines was emitted at some wavelength. And so we can see how much redder it's gotten due to that recessional velocity. And then on the vertical axis here, I put distance. This is one of the trickiest things in cosmology to measure. And so we have to use some tricks to do that. Often in a lot of measurements, and you'll notice later in the talk, I'll start using this cosmological redshift velocity as kind of a proxy for distance. They're not exactly the same thing, but it's an easier thing to measure. For distance measurements, we use a couple of unique objects in the universe. One example I'll mention is a type of supernova explosion called a type 1a supernova. This is a particular explosion that happens at the end stage of certain stars' lives that has this unique property that they seem to all occur at basically the same intrinsic luminosity, so the same inherent brightness. And so as this little cartoon is illustrating, we call these standard candles, because if you know these things are all the same inherent brightness, we can look at the flux, or we can look at how bright they look when we observe them to tell us about their distance. So the brighter of these objects that look brighter in our measurements are going to be closer. The ones that look fainter are going to be further away. So if we collect enough measurements of these supernova and distant galaxies, we can measure the velocity, we can measure the distance, and we can make a plot of these. And I'll add some other lines to this plot in a second that are a little darker, but this right here is basically, there's a straight line that says constant expansion, parentheses, straight line. And this is the idea that if the universe was expanding over time at the same rate, so it takes the same, so the rate at which space is expanding doesn't change over time, then there's a linear relationship between these things. So a galaxy that is twice as far away has twice as much space. So if galaxy B is twice as far away as galaxy A, there's twice as much space between galaxy B and us than A. If that space is expanding uniformly, twice as much space means it's moving twice as fast. I don't know, I'm talking in circles a little bit. You get a straight line on this plot if expansion is constant. All right, why are we interested in this? We are interested in this because we have a theory of gravity that relates the expansion of space, or the behavior of space-time, to the mass and energy that occupies that space-time. And we can solve some equations and find that if in a universe with gravity described by general relativity and where the mass and energy density is dominated by matter, we actually expect that expansion to be slowing down over time. So you can think of everything's thrown out in some initial Big Bang, and then the mass attracting mass, or the matter in the universe, the gravitational pull among that matter kind of acts as like a friction or like a braking to slow down that expansion. And what that would look like on this plot is for a galaxy at a given distance, which remember is telling us about a certain time in the universe, if the expansion of the universe is slowing down, it means that at that time in the past, it's moving faster than it would be at a constant rate. So this line kind of peels down away. So like you can kind of throw some horizontal lines on here to say like, object at a given distance, how does it compare to a constant expansion rate? So in the late 90s, there were several teams working to make even more detailed, even more distant measurements of supernova to constrain something called the deceleration parameter to study, exactly how much matter is in the universe, how much is this decelerating. And to the surprise of everybody, I found that the expansion of the universe was not decelerating, it was accelerating. So instead of finding this line kind of peeling down from our straight line, it's going upwards. It's telling us that the expansion of the universe is actually speeding up. And this was a big deal for a number of reasons, as a bit of evidence that this discovery from the couple of teams that first made this finding won a Nobel Prize in 2011. So why is this a big deal? So finding that the universe is accelerating, excuse me, is like if you threw a ball up in the air and instead of having it fall back down towards you, it like zips off in some other direction. For the universe to be accelerating or for your baseball to fly off into some unexpected direction, there needs to be some source of energy driving that acceleration. And so hence, this is what we call dark energy. We don't know what it is, but we can test different models for what properties it would need to have to give us this accelerated expansion. And by far, the simplest model or the simplest thing that could cause this accelerating expansion is something called the cosmological constant. So there's some interesting history here where like Einstein initially introduced this into his equations for general relativity because he didn't think the universe should be expanding or not at all. And then once Hubble found that the universe was expanding, he's like, oh, we don't need this term. That's maybe a narrative for a different talk. But just to say, it wasn't a completely new idea, but it had been, well, I'll just say what it is first. So cosmological constant is basically an idea that energy space has some inherent energy density to it. This is something that our friends in particle physics do predict. So if you take your theory of particle physics and predict what you expect the vacuum energy to be or what the cosmological constant to be, you get a number that's so wildly different from what we measure in cosmology that it's like, I don't know, it's like 10 with 120 zeros after it factored in. It's an absurd difference. So like this is an area where there's definitely a place where our understanding of general relativity and particle physics don't quite match up. So one of the big mysteries for like, if dark energy is a cosmological constant, why is it, like, if you think of like nice symmetries in our universe, you'd think it would either be zero or something like we'd expect from particle physics, and not this thing that in that sort of absurd scale of numbers is something that's really tiny, but not quite zero. You know, really tiny, but it's still 70% of the mass and energy in the universe, which, you know, I guess just tells us that particle physicists think in different energy scales than our day-to-day lives mostly. So yeah, cosmological constant, inherent energy associated with empty space is sort of the simplest description we can have with dark energy. In that model, it would be the same energy density everywhere in space and constant throughout time. So cosmological constant is constant in space, constant in time. You can also try to cook up models for it being some substance or some like field pervading the universe that has some properties that might not be constant in time, but are sort of tuned to give you that accelerating expansion behavior. You could also ask, is this accelerating expansion a hint that maybe we need to extend our theory of gravity by extending general relativity sort of in a similar way to how general relativity expands our understanding of Newtonian gravity? So these are a lot of big questions. And I'll just note that these last couple of years, so like the last 2 to 3 years, have been a really exciting couple of years in dark energy science, in that since dark energy was first discovered in the late 90s, pretty much all observations have been finding results consistent with cosmological constant dark energy. And just in the last couple of years, as we're making more and more precise measurements of expansion history of the universe, there's a couple results which seem to be hinting that maybe it doesn't have constant in time. There might be some time-dependent properties. None of these results really passed the threshold yet to like an all-out discovery. And it's also new analyses with new measurements. So like as a community, I think we want to definitely more deeply understand this. But it's been it makes it a newsy time for thinking about dark energy. So we're working towards making more precise measurements of expansion, in addition to measuring the expansion history of the universe as a cross-check. Well, we can also think about measuring structure in the universe, or the clumps of matter in the universe. So that's the I guess where I get the title of clumper. Okay. So I'm going to shift into talking a little bit about how we approach testing this with like observational campaigns, these galaxy surveys, but this would be a good point to pause if anyone has any questions.
If I say nothing, you can go faster, you fly higher.
Mm-hmm.
So if the universe is basically nothing, bunch of stuff. And the nothing is expanding faster than the speed of light. Could it just be dragging stuff along with it?
That's a good question. So the sort of the physical speed limit of the speed of light corresponds to how fast stuff can move locally, like relative to like the space-time it exists in. So when it's like the space between two objects is expanding, those two objects can be moving apart from each other in some coordinate system faster than the speed of light, but neither of them in sort of their local environment is breaking that speed limit.
At the bottom of that cup there, at that point, nothing is certainly expanding faster than the speed of light.
Mm-hmm.
And dragging everything with it.
Yeah, that's an interesting thought. Yeah, so this is a little cartoon showing basically the evolution of the universe, where the vertical size is meant to illustrate sort of the overall like expansion of the universe, and then time goes from left to right. And yeah, once you compress things to a small enough space, you get to like high enough densities, and you makes the universe be at a high enough temperature that's somewhere where our understanding of like particle physics starts to break down. So there's a little bit of a here there be dragons region to the left there. So most of the stuff that I'm going to be talking about is this way. Yep. Oh, sorry, we had a question in the back.
If you just imagine that you're sitting inside of this, maybe an expanding sphere that has the density of a black hole all the way around where it's small.
I'm not sure I fully follow your question. Could you restate, or I'm happy to follow.
The expansion would be as things get further out, they start approaching. Then eventually you can sort of try to model that as a sphere of black hole density around you. And
Okay, yeah, so I think there's maybe two points to make here. One is that it's a bit of a confusing thing where you say like, you know, if everything's expanding, what is it expanding into? And in sort of the analogy, I'm not going to skip back to the expanding balloon. Well, I guess that's tricky because the balloon. Yeah. So it is really that all of space is expanding. There can be different. We can like test for like the geometry of the universe to see if it's sort of spherical or hyperbolic or flat. But at least as far as we can tell from observations, there's not like, and things seem pretty uniform even when you look pretty far out. A point that I would add there though, but because light has this finite speed, there is going to be some distance away in the universe that we'll never see light from because of the way the universe is expanding. And in that sense, you can sort of model the certain distance in the universe is kind of like an event horizon, like you would have in a black hole, because like no information can be transferred. I don't know if that touches.
you will be accelerating at the same rate as if you're 1% of your like what? I would be curious how different that acceleration curve looks like.
I think that's. I think that there's probably something with like spatial uniformity, but I'm happy to follow up maybe after the talk if you want to chat more.
Yeah. Yeah, I just was wondering, was there anything other than
So I believe we're really relying on Doppler shifting there. So there's a couple different ways we can measure that. So you can look at absorption lines in gas, or you can look at the spectra of stars. So there are some independent probes, but it is relying on the shifting of like spectral lines.
Yeah, I'm just curious about, there's a lot of mass in black holes. So sort of where do they fit when you're trying to figure out how much mass is in the universe?
Yeah, so they go in the matter section. So generally, astrophysical black holes, which mean that black holes that are the endpoint of like some massive star's lifetime, initially that mass was in visible matter. hydrogen, helium, and then whatever it gets burned into through nuclear fusion. And that gets conserved, where some of that will get blown off into gas and dust in the universe. Some of it goes into a black hole. There are models that people study for, like, is there some population of little black holes left from the early universe? But the key thing for how we figure out which category to put things in here is, how does the density of the substances change when the volume of the universe expands? So if you have a certain number of hydrogen atoms in a box, you double the size of the box, your density is going to go down by a factor of 2. Same with if you have a box with some black holes in it, the density of your black holes is going to scale the same way like hydrogen atoms would. And that turns out to be the important feature for how the properties of stuff interacts with the expansion of the universe. This is, I guess that's a nice example to just illustrate how weird dark energy is. If it's like something that's like a constant energy density of space, you have a box, you double the size of the box, your total amount of dark energy has doubled because the density stays the same. And that is strange and breaks a lot of physical intuition.
And that's if you're in this galaxy per box, not like.
Could be either. So no, generally things that are gravitationally bound, so like mass and galaxies or groups of galaxies that are like orbiting each other, those will stay bound together and will not expand. It's when you get into regions where the average matter density in a region from galaxies, black holes, and whatever is smaller than the dark energy density, then you have this expansion dominating. But if you have a region where like the local density of matter dominates, things can stay like tied together. So in a sense, we're also lucky that, I said the dark energy density is this, in some units, very small but non-zero number. If it was much bigger, if it was like a particle physics size number, that sort of balancing act between like where can matter density dominate and let things clump together gravitationally and where is space just going to expand, that would be off. So if the dark energy density was like particle physics numbers, you probably wouldn't even, I don't remember, you wouldn't be able to form planets, you probably wouldn't even be able to form atoms. It would be a very different universe. So we're very happy to live in a universe with small but non-zero dark energy. Okay, I'm gonna jump back into this. So when we think about trying to characterize the properties of dark matter and dark energy using observations, we generally do this in a framework of testing different versions of a cosmological model. So this is, we have some set of ingredients which include descriptions of includes several ingredients. Important set is, our pie chart here. It's some description of what does dark matter act like, what does dark energy act like. So, a simple cosmological model. I don't think I have it anywhere in this talk, but I'll just mention the sort of standard cosmological model is something we often call lambda CDM, where lambda refers to cosmological constant dark energy. CDM means cold dark matter, which means dark matter only interacts gravitationally and the particles aren't moving very fast, hence cold. But if you have some description of dark matter and dark energy, an alternative model could be dark energy with some time dependence, or dark matter with a little bit of some like weak nuclear force interaction, or you can cook up a variety of things. Another ingredient is our theory of gravity, which again, in sort of our standard approach to this, is the theory of general relativity. And then if you add in some measurement of the current rate of expansion of the universe, that's enough to predict the whole expansion history of the universe, which we can then compare to measurements like our supernova measurements or other ways of probing expansion history. Another thing we can do is describe the evolution of density fluctuations in the universe. So when I'm talking about expansion history, we're talking about sort of the overall average properties of the universe, like average matter density, mass per volume, or average amount of dark energy per volume. But we know from experience that the universe is not uniform. We're very grateful for that. Since we live in an overdensity, we are overdensities in the universe. So as part of this set of ingredients we need to be able to predict what this will look like, we can input some description of what small density fluctuations in the early universe look like. And given all of those things, we can make a prediction for how tiny density fluctuations in the universe grew under the influence of gravity over time. The idea here being, if there's a location here in space that has a little bit more matter in it than this location over here, gravitational force will pull more stuff into the high density region. And so you go from having an almost uniform universe with, you know, like a tiny amount more matter here than here, to a universe that contains things like, you know, galaxies and observatories. And we can probe the properties of those structures in a couple ways. A bit of this cartoon that's not showing up super well on the slide is one way that this shows up is in tiny temperature fluctuations in light that we observe coming from the early universe. If you're familiar with the term, this is something called the cosmic microwave background. If not, it's an observational handle we have on like what density fluctuations look like only like when the universe was only about 300,000 years old. So early universe measurement. And then the relatively later universe measurement, we can look at how galaxies trace over densities and how those have evolved over time. And so those gives us two big lever arms, so an early universe measurement and a late universe measurement that lets us test how well a given choice of the ingredients matches our measurements. And we can, you know, pick a couple different choices for the ingredients, test them against observations, and work towards ruling out some things that dark energy and dark matter can't be, or at least ways they can't behave, and hopefully find some clues for, if we can describe how they behave, we can work towards trying to get a better understanding of what they like fundamentally are.
Most of these models, that's post-inflation. But you don't have to do it.
Yeah, so inflation is this very dramatic period of rapid inflation in the early universe. Generally, a consequence of this inflation would be if the universe expanded really, really dramatically fast in the first like 10 to the minus 30 something of a second, you get this behavior where quantum fluctuations just in like whether there's a particle somewhere or not get stretched out really dramatically to become classical fluctuations. And so a pretty common set of ingredients for these initial density fluctuation properties, like how big density fluctuations are in different scales, is an output of sort of this paradigm of inflation. So one of the things that I don't personally look at a ton, but people do test, is saying like, if whatever quantum fluctuations source these had some additional interactions, that'll give you some different statistical properties to these early universe fluctuations that you can then try and go look for. So that's baked in here as well. But yeah, generally the we know how to compute what this implies starts well after inflation. So we just start with like an assumption for like the spectrum or like the statistical distribution of those density fluctuations.
What's the time dimension of that bell?
I cannot promise it is not to scale. It is definitely not to scale. So this is about 14 billion years, but this is like 400,000 years from here to here. So this is a very schematic. We are here. What's that? It's really at the end of it. So like I've tried to draw here where it's expanding sort of more gradually, and then it starts to widen up a little more sharply. And that's supposed to depict when, thank you, dark energy starts to dominate the matter and energy density. So where the accelerated expansion turns on, which is about 2 billion years ago from our mapping of expansion history. 2 billion? About, yeah. Yeah, so the accelerating expansion, cosmologically speaking, is like fairly recent. But you know, on human timescales, it's been around for a while. But for a lot of the history of the universe, it was actually the matter density that dominated. And then, you know, as we said, as space expands, you don't change your number of like particles, so you're diluting the matter as space expands. And eventually, at some point, that means your matter density drops low enough that it's below your dark energy density, and that's when the acceleration kicks on. And so as we move forward in time in the universe in the next couple of billion years, the matter density will continue to get smaller. So if we look at a snapshot of this pie chart in like 2 billion years from now, these matter wedges will get smaller and the dark energy wedge will get bigger. And so we'll move more and more into this acceleration. Okay. So I think I've given you a bit of a gist there that we want to measure and map the structure, these density fluctuations in the universe, to learn about these fundamental physics questions. And I just want to like underline why, well, that these density fluctuations carry information about fundamental physics because what they look like and how they evolve over time is going to depend on that physics. So, you know, it's maybe kind of straightforward that, well, what you start out with, what those little initial density fluctuations in the early universe look like, that'll dictate what they turn into in the late universe. Gravity is causing the clustering, so if you change how gravity behaves, it's going to change how this evolves over time. It is matter doing the clustering, so if matter behaves differently, the clustering will look different or can look different in certain ways. And maybe a little less intuitively, like the expansion of the universe will also influence the evolution of this, we call it large-scale structure. It's a structure on large scales in the universe. And the sort of, to build that up, it's this idea that if the space between two clumps of matter is expanding, it's a little bit harder for them to fall towards each other. So if you turn the dial on your cosmological model and increase the amount of dark energy, the time that accelerating expansion takes on starts making it harder to have, us to go from this more uniform thing to this more clumpy thing. And so it'll kind of act as a friction or kind of turn off the ability of matter to continue clumping, and you'll kind of stick with the clumps you have.
Would the red cube be getting bigger?
Right, so these are images from a simulation, and they've been scaled so that it's like the physical space size of it is getting bigger, but they've just been rescaled to match like a certain like coordinate that is expanding along with the universe. Good question. Okay. I'm talking about large scales on the universe, so it maybe is good to think about what we mean by large here. And when I'm talking about large scale structure and when we measure this with galaxy surveys, we're looking at scales of the universe that are big compared to individual galaxies. And so what this image in the background here is showing, it's also actually a little bit pixelated, but a snapshot from a simulation of these matter densities forming. And in the simulation, the matter density is colored, the brighter spots are higher density, and the darker spots are lower density. And so you see you get this filamentary structure with these like bright spots at the nodes. And sort of these bright spots are the high density regions where you form like clusters of galaxies. And the nice thing for us in terms of data analysis and our ability to model things is when you zoom out to these large enough scales, or what we consider like cosmological scales, we can start describing the structure of this matter distribution statistically. So we're not trying to predict, I'm going to see a galaxy right here if dark matter and dark energy behave a certain way. We say, if dark matter and dark energy behave a certain way, I expect a certain number of peaks, or I expect these like filamentary structure to have a particular size. So we're thinking statistically here. And the scales where that we can describe the universe in that statistical way, I've presented in a number of different units. So I think the most intuitive thing is to compare light travel times. We're talking length scales that are bigger than about 30 million light years. And just to compare that, the distance to Andromeda, which is the nearest galaxy, is about 2.5 million light years. So we're looking at scales that are, I don't know, if you draw a circle or a sphere in the universe with this as a diameter, you're going to have a bunch of galaxies in it, as opposed to just like one or two. And these intergalaxy spacings are way bigger than individual galaxies and are much bigger than spacing between stars in our galaxies. Include kilometers because why not? But those numbers are so big. I don't know about you, but I can't understand them. I include parsecs because this is what we normally talk about in cosmology. So if I slip up and say like 10 megaparsecs, it's about 30 million light years. Okay, so large scales means very large scales. So it turns out when we observe distance of the universe, we really only measure it up to a factor of like what the current expansion rate in the universe is, which has some uncertainty. And so we absorb that into our units in a particular way. So
H is what?
About 0.7. But in practice, most of our observations have it baked in there. So if we're comparing measurements to predictions, if we leave it in the units, it keeps everything on the same page and we don't have to like correct out which number we've assumed for that. But that's cosmologist units.
What does that say? 500 megaparsecs per H?
Yeah, and so if you wanted to take out the dependence on the current expansion rate of the universe, you just plug in a value for little h that is around 0.7. Yeah. Depending on which measurement you pay attention to, it might be 0.72, it might be 0.68, we're not quite sure. So we leave it in there to make sure we're always comparing apples to apples. Yeah, it's the Hubble constant divided by 100. So Hubble constant is usually written with a capital H. We divide it by 100 and get a little number and write it with a little h. I don't know. Yeah, it's a little bit technical point, so I'd say don't worry about it here, but it's you know. Okay, so given our model for the physics of the universe, if we have some model for dark energy, dark matter, we can make a prediction for the statistical distribution of matter in the universe. There's one catch, which is our prediction is really for the total matter density, or which is mostly invisible dark matter, which we can't see, you know, by definition. So if we want to learn about the matter distribution in the universe, this is kind of like trying to infer like where land on Earth is based on an image of Earth at night by looking at like lights and cities. We can use the fact that galaxies form in high density regions. So visible matter tends to trace dark matter, not exactly, but to a well enough precision, we can use observation of galaxies to learn about this hidden, the majority of matter which is hidden. And so this is also another pretty simulation image where again, here the dark gray is the dark matter density. And then the sort of yellowy blobs are some galaxies that have been added to the simulation, showing you that like each of one of these specks would be a galaxy. And so here's a really big cluster of galaxies in the simulation. So we're using these little specks to try and learn about this like web-like structure. And that brings us to galaxy surveys, which are observational enterprises to try and do this. And there are two broad types of galaxy surveys. I'm going to be focusing mainly on galaxy imaging surveys. I'll mention what the other one is in a second. This is what I mainly work on. And so as this sounds, what a galaxy imaging survey is you systematically take images of a big portion of the sky and try to do so as uniformly as possible so that you can then find galaxies in your images, like beautiful image of a galaxy. Also, all these little dots, which are also galaxies, which are actually most of the galaxies that we observe are the little smudgy dots. And there's a few of the big spirals that are very pretty, but you know, if we're in the statistics games, we want high numbers, so we go after the little specks. And we can analyze the distribution of galaxies to learn about the dark matter. You know, for when maybe it's cloudy and the sky here isn't available, this website, legacysurvey.org, has a really cool viewer which collects data from a bunch of different galaxy surveys where you can like zoom around on the sky and like zoom in to find different galaxies and things. So it's very fun to play with. And so this is just a screenshot from that. And generally speaking, these galaxy imaging surveys are done. There are some upcoming that are space-based. So the Euclid Space Telescope just launched in the past year is going to do an imaging survey from the European Space Agency. The one that I'm particularly excited about because I am in this collaboration is the Rubin Observatory, which is going to conduct something called the Legacy Survey of Space and Time, or LSST. And it has the claim to fame that the LSST camera is the largest digital camera in the world. And it got installed on a telescope in Chile just about a year ago. And Rubin Observatory is named for Vera Rubin, who we heard about with the galaxy rotation curves. So yeah, I'm involved in two galaxy survey collaborations that are imaging surveys. Depending on time, I'll tell you a bit about analysis I've worked on in one that finished taking data in 2019, and we just put out some cosmology results like 2 months ago from a survey called the Dark Energy Survey, and then the Rubin Observatory, or LSST, is coming up and is going to start observing later this year. Yep.
How much time does it take to do each image?
So each image, I'm not sure for Rubin, I think for dark energy survey, each image, I might actually have another slide here. We take about a 30-second image in each of the 4 or 5 different color filters. So these giant digital cameras on the telescope don't have different sensors for different colors. You're just collecting all the photons that go into it. And to get color information about the galaxies, what we do is we put a filter in front of the detector and measure the light that gets through, which tells you how bright is this galaxy in some different color filters. So this is kind of a mesmerizing animation of the filter changer on the Rubin Observatory. And the little illustration of like a galaxy will look like where the light is coming from will be a little bit different in different color filters based on the spectrum. With these surveys, this is how we get some like line of sight redshift or distance information. And this is a little bit of a technical plot, but trying to illustrate that what these black lines are showing, there's 3 sets of them. There's a solid line, a dashed line, and a dotted line. Those are meant to be the spectrum of some galaxy. So how bright it is at different wavelengths of light, if it was at different distances along the line of sight. So if it's further away, its colors are shifted more towards longer wavelengths. So you can see that the solid line is here. It shifts a little to the right for the dashed line. It shifts a little more to the right for the dotted line. And when we look at it through different filters, which are what these colored bands are, when we look at a galaxy through a filter on a telescope, we're saying, how bright is it? Like how much light is in this chunk of the spectrum versus this chunk versus this chunk. And so it's not an exact process to infer the galaxy spectrum or its exact redshift bias, but we can, with some like machine learning type methods, make some decent guesses with some pretty significant error bars for what the line of sight distance or what the cosmological redshift for galaxies are. So we can get a little bit of line of sight information, but we're mostly making maps of images of galaxies on the sky. That's in contrast to this other kind of galaxy survey, which I'm just going to touch on for this slide, but I do want to note, and this is something that a lot of folks over at OSU work directly on, is a spectroscopic survey. And the idea of a spectroscopic survey, this is the same plot as before, is rather than getting color information by imaging in different filters, is you point an optical fiber at a galaxy and point it at enough time to collect enough light to actually map out what the spectrum is or what this black line would be. To do this, you generally have to take some images of galaxies, pick some targets to point optical fibers at, and you end up with, you can't get as many galaxies because it takes longer to get a good spectrum than it does to get a decent image, but you can get a lot more precise information about the line of sight position of galaxies and make like 3-dimensional maps. So this turned out to be really great for measuring expansion history stuff. And so new measurements of this from a survey called the Dark Energy Spectroscopic Instrument, I told you they all have dark energy in the name, is behind some of these very newsy results about potentially time-dependent dark energy. And I really like this animation. What this is part of the focal plane of that telescope. Instead of having a CCD or like this chip that like you have in a digital camera, it's this plane of several hundred of these little robot arms, each of which has an optical fiber in it. They're each about the size of your finger, and they can point at different galaxies. So this is letting this survey really get an unprecedented number of spectra. Previous iterations of this would have a like metal plate with holes drilled in it that somebody had to go plug in fibers to by hand. So this is like dramatically increased how many galaxy spectra we can get. So I'm not going to talk more about this other than to note this is very cool. You know, these different types of galaxy surveys do provide complementary information.
Is that currently being used, or is this?
This is currently being used. It's made, cosmology results are out for their first 3 years of observations. I think they're going to have 5 years total, but have already gotten funding to like extend beyond that and keep going. So yeah, this. Yeah, so this is at a Kitt Peak Observatory in Arizona. The Mayall telescope, I think, is the name of it. Yeah. Okay. How are we doing on time? Are we happy with like 10 more minutes, or are we? Okay. 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 All right. So while I've said that getting spectra is exciting, the thing that you get with imaging that you don't get with spectra is being able to measure galaxy shapes. And this is particularly interesting when we're trying to map the distribution of invisible dark matter in the universe. And that's because it gives us some information about gravitational lensing. So light, when traveling through a gravitational field, can get deflected. The deflection of light through the sun's gravitational field was some of the first evidence that general relativity in fact worked as a description of gravity. And this is happening throughout the universe. So in this little cartoon, we've got a set of distant galaxies. We've got a clump of matter with some other galaxies in between us and the distant galaxies. If this clump in the middle wasn't here, the light would just travel in a straight line from where it originates to our telescope, and we'd see an undistorted image of our distant galaxies. But what happens, in fact, is the light, as it moves through the structure in the universe, you can picture in those simulation maps, we have all these filaments. So when any filaments of matter clumps in the universe, and when light travels through that, it'll get deflected a little bit. And that'll result in distortions in the apparent shape of galaxies that are oriented around these matter overdensities in the universe.
Did you say that dark matter does or does not lens?
Dark matter does lens. So anything that acts like matter gravitationally does do this lensing. So this is exciting because, you know, the mass that's in these galaxies, but also the mass that's in the dark matter around these like intermediate galaxies will contribute to distorting the background galaxy images. This is a dramatically exaggerated cartoon. If you quantify like the ellipticity of galaxies, like how much are they an oval rather than a circle, the effect of this weak gravitational lensing is generally like less than a percent of the like ellipticity of the galaxies. So this isn't something, if you just observe a set of galaxy images, you would have no way of knowing what their what part of their shape is intrinsic, what part of it is due to lensing. But the powerful thing here is that galaxies that are nearby each other on the sky, their light's traveling through similar structure. And so the distortion to their shape is that structure, that gravitational lensing, how it distorts their shapes is going to be coherent. So galaxies are going to be distorted in a similar way. So one thing you can ask is you can say, how does, if I say that this little ellipse is associated with some direction like this, and this one is like this, and this one is like this, you can ask how aligned are the shapes of galaxies as a function of how close or far apart are they on the sky. And, you know, as I said, we're in a statistical regime. If you measure enough pairs of galaxies, their intrinsic shapes will be basically random, and so will all cancel out. But what you'll be left from that averaging is going to be that coherent alignment from the weak gravitational lensing. And so in practice, when we measure this, so with the dark energy survey, we do this with like 140 million galaxy shapes. So we work with very big samples to be able to pull this very subtle signal out to learn about this gravitational lensing. And for that, you need like very precise imaging information. You need a good understanding of what the atmosphere and your instrumentation is doing to your image. And this is really a big collaborative effort with a lot of institutions and scientists involved. So I'll do a quick little zip through some of the DES work that I've done. So I've been a member of the Dark Energy Survey for about a decade now. I joined at the right time to go do a couple of observing shifts. So this is me at the telescope in 2017. I mostly work in theory and data analysis. So it's, if I had been in cosmology much earlier, I wouldn't have known enough for somebody to let me push buttons on a telescope. It was like nicely automated by this point. My job was mainly to call somebody if something went wrong. But it was a very special experience. So yeah, so DES was a 6-year survey operated from the Blanco telescope in Chile. And there's something like 400 active collaborators working on different aspects of science. And I feel very lucky to have a lot of wonderful people I've worked with. And this is what it looks like inside the dome. As with the Rubin Observatory, there's a custom-built giant digital camera. On the telescope, the camera is up at the top here. Again, it's a similar technology to what is in like your digital camera in your cell phone, but instead of being a tiny chip, it's like this big across. To Together, the survey did 758 nights of observations over 6 years. So that's why they even let Ceres go push buttons on the telescope. So they need people to cover those nights. And we've released cosmology results, the analysis results in stages, and our cosmology results from like structure measurements from the full 6 years just came out this past January. So it's been a long road, big effort. There's still science to come. And this is just to give a little illustration of what we do when we do a survey. So this is an actual image from the DES camera. So there's a lot of little blurry dots, but note that this is what one exposure of DES looks like. Well, I guess it's a couple because you can see colors, which means we mix together images with different filters. But this is just to note that the field of view of this telescope is several times bigger than the full moon. So we have a big field of view, which means we can cover a lot of the sky relatively quickly. And so if we represent that exposure with a hexagon, we can go and take exposure, 30 seconds at a time across the night and work on tiling the sky. And we have a footprint that we cover that this is a slightly cartoony image of, which it's kind of a funny shape. And I eventually have a picture of this next to the galaxy, but basically it's a big circle that's looking out of the southern plane of our galaxy. Because turns out if you're trying to look at distant faint galaxies, the Milky Way is something that gets in our way. So we have to look outside the plane of the galaxy. And then there are some rectangles added on to increase overlap with some other kinds of measurements that let us do complementary science. It is. Okay. I'm going to zip through this a little bit quickly since I already introduced weak lensing to say we can make several kinds of statistical measurements with this. As I said before, one of the measurements is we look at alignments between galaxy shapes. This is called weak lensing, or sometimes we call it cosmic shear. Shear meaning distortion to the galaxy shape. We can also use the fact that galaxies form in overdensity, so we can look at the clustering of galaxy positions, like how likely are we to find galaxies separated by some angular scale in the sky versus another, or compared to what you would expect if they were just randomly distributed. And that's using the galaxy locations to tell you about where the dark matter overdensities are. And then we have galaxy positions and shapes, and we can look at the relationship between those. So here in this cartoon, it's like the red galaxies are in the overdensities that are lensing the yellow galaxies. And so we have these different ways of analyzing our galaxy images to get complementary images. The positions and shapes have different kinds of uncertainty. So we put them together to try and hone in on the physics. And putting that together, we can make a map of where the dark matter density is in the universe. So here's our little tank shape again of the survey footprint. And what this is showing is based on our galaxy position and weak lensing measurement, in this purple region with the lighter regions meaning more density, this is what we've inferred to be the projected matter density in that direction on the sky. So this whole oval is kind of like, a globe gets projected onto a wall map. This is like looking out at the sphere of the sky, flattened into, I think, a MOLED projection. So we can see our Milky Way galaxy here. We've got some Magellanic clouds, which we're trying to avoid because they're also hard to look through. And so we've mapped out this matter density in this region, which covers about 1/8 of the total sky. We can also translate that into telling us something about our ingredients in our model. So I don't need to get into this in a ton of detail, but this is just to show this is what a lot of the results in our physics papers look like, where it's given our assumed model and our measurement, we can try a bunch of different values of ingredients of our model. So here, this is matter density, how big is that matter piece of that pie chart? And this is a parameter describing how clumpy the universe is and how clumpy the matter in the universe is. And the gray contour is showing, based on the galaxy survey data from the Dark Energy Survey, what parameters give good agreement with the data versus bad agreement. Good agreement is in the darker ellipse. And we can compare that to similar inferences from the early universe. And the idea here is that this red contour is telling us we've made these measurements of light from the early universe and learned about what density fluctuations looked like 300,000 years after the Big Bang. And we've used our cosmological model here, like a sort of the simplest standard cosmological model, to say, given these early universe density fluctuations, what do we expect the late universe to look like? And so when we compare these constraints, we're testing the ability of that model to predict about 14 billion years of cosmic history. So the fact that they're even in the same region of a plot is pretty remarkable. And then you can also squint and be like, all right, one's a little lower than the other one. Statistically speaking, these aren't really strongly in tension, but there are a couple other measurements of the late universe that are similarly offset. So this is something, along with these interesting dark energy results of the past couple of years, that we are looking into more. And so we test our model by comparing different data sets. We can also consider adding new physics to the model. I think this is the last cartoon I'll subject you to. But this is to say we're looking for tensions between different measurements and tensions between sort of the simplest versions of our model and our measurements to find clues for how to make a more fundamental description of dark matter and dark energy. And this is the cuteness here is that, you know, if our simplest model, when we've observed a billed nose and a webbed foot, is that we're looking at a duck, and we go find a new piece of data that says the tail does not look like a duck's tail, it looks like a beaver's tail, that might tell you you need to revise your model and find that you have a platypus. So, you know, is dark energy a cosmological constant, or is it a platypus of some kind? And so as a community, we're working towards making sure we really understand these measurements. So we get more and more data, error bars get smaller, which means when we make model predictions to compare to that, we have to be really careful that we understand all of the uncertainties that go into that. That's what I spend a lot of my time worrying about. And, you know, we want to explore, you know, if dark energy isn't constant, what could it be? And I'll just end on noting that exciting physics is both literally and figuratively on the horizon. So this is an image from the DES observing site. The Rubin Observatory is literally one mountain over. So this is when I was on observing shift, you could see it under construction. And the Rubin Observatory is going to observe about 30 more times galaxies than DES. It's going to image basically the whole southern sky every 3 nights over 10 years. And throughout my career, this has been this thing that's happening. Eventually, it turned on last summer. So we're getting science commissioning data right now. The actual full survey is supposed to start later this year. This is a picture from the New York Times science page that I have a paper copy of framed in my office. This is just to say, you know, we've learned a lot. There's more to learn. This image here, I think, well, it's the Trifid, yeah, some nebula. So it's one of the first images that was taken with the camera when it was working on the telescope. So they picked something pretty to point at.
Can you identify the different colors?
Well, stars are blue and hydrogen is pink, according to the caption here. So the pink corresponds to hydrogen emission and the blue is stellar emission. So again, this is a false color image based on the light through these different filters, but sort of representing different emission in that nebula. So that's, I'm pretty sure that's all I have. Nope. Okay. Yep, that's all I have. So I'm happy to take more questions, but I know I've kept you a little bit long anyway.